What really controls the flow of electricity through systems and devices? In this video, we'll break down electric current, resistance, and the hidden rules that govern how energy moves through a circuit. From microscopic electron drift to the mighty power of Ohm's law, this is the heartbeat of every electrical system. Electricity is the movement of electric charge, typically carried by electrons through a material. As a reminder, the electric charge has the letter Q, could be capital or lowercase, and this is always measured in units of coulombs. That's what we measure our electric charge in, and the charge could either be positive or negative. Even though the electrons are the primary charge carriers, we also can think about the motion of positive charge carriers as well, and the charge of an electron is 1.6 times 10 to the negative 19 coulombs, and for an electron that would be negatively charged. That's just a little bit of review about how charge is stored in materials. And so the image that we want to have in mind for this unit is thinking about a copper wire here, where we have a metal encapsulated by some type of insulating sheath. Inside of that wire, there are small individual atoms, each composed of a nucleus of protons and neutrons, which are positively charged, with small electrons that are negatively charged orbiting around that nucleus. And within this lattice, this arrangement of copper atoms, the electrons are free to hop from one atom to the next, and this is one way that charge can be transferred within a material. Electric current describes the amount of charge transferred every second in some type of electrical system. We use the letter I for the electric current, and the equation would say a change in charge divided by a change in time. So if I have some battery outputting a certain amount of coulombs or charge into this light bulb, I could describe how many coulombs were passing through that light bulb every second with the electric current. And current has a new unit called amperes, which has the letter A, and this is really just a coulomb per second. Now, the current does have a direction. It is technically a vector. It could either point right or left. It could either be traveling counterclockwise through this system, or it could be traveling clockwise. In this case, our current, conventionally, we always say to be the direction that positive charges would move. So from this battery, it's got a lot of positive charges on the left side at high potential. Those positive charges will want to move through the circuit, powering the light bulb until they can recombine in the end with all the negative charges at the low potential end of that battery. So in other words, current always measures the motion of positive charges. Even though electrons are negatively charged and they're the primary charge carriers in most systems, the conventional current is labeled to be the direction of positive charges. So if charge carriers are moving when they are experiencing an electric current, then they must have a velocity. In reality, a charge carrier like an electron doesn't follow a straight path through a material. Owing to the nuclei in the material being sort of scattered around, the electrostatic attraction between the negative electron and the positive nucleus will cause for the electron to sort of bend its path as it traces its way through a material. But overall, it does have a certain directionality to it. Overall, it's working its way through the material. And so we would say that the average velocity that is felt by a charge carrier in a material is called the drift velocity. This is the average velocity that a charge carrier would experience by an electric field forcing it through a conductor. The unit of drift velocity, of course, is meters per second, and the drift velocity is related to the electric current through this equation, where Q is the charge of the charge carriers, N is the carrier concentration measured in inverse meters cubed. This is like the number of charge carriers per unit volume. A is the cross-sectional area of the material, and VD is the drift velocity. Under normal conditions, a metal would have electrons sort of scattered about and nuclei scattered about, and there would be no overall direction of motion for the electrons. But if we establish an electric field by putting a low potential on one side and a high potential on the other side, then the electrons in that material will feel a force due to that electric field and will ultimately start to drift one way in the material. And so you can see that when we turn on the electric field in the bottom right, that the electrons begin to feel a force and are accelerated to the right. But as they follow that path, they're bent a little bit by each next nucleus that they pass. So let's try an example. Here we have an incandescent light bulb filament made of copper with a cross-sectional area of 2 millimeters squared and a electron charge carrier concentration of 9 times 10 to the 28 electrons per meter cubed. The question is, how fast do the electrons move through the wire? So we'll start with our standard problem-solving strategies. We will draw a diagram. So let's imagine that our copper filament is a perfect cylinder, and the area of that cylinder we would call 2 millimeters squared. Don't forget that if we were to convert that to meters squared, it's not just a simple dividing by 1,000. We need to make sure that we don't forget about that squared in there. So really, this number ends up being 2 times 10 to the negative 6 meters squared. Now, the charge carrier concentration, which tells you about how many electrons there are in here, we'll label as 9 times 10 to the 28 inverse meters cubed. Really, that's like electrons per meter cubed, but we don't write out the unit for the particles. We were also given that the current flowing through this filament is 1 amp, so there is our current value. And it's just asking how fast the electrons move through the filament under these conditions. So in that case, our drift velocity would be our variable that we're trying to solve for. Now that we've labeled our knowns and unknown variables with units in the standard units for all of the variables, we can find an equation, rearrange, and solve. The one that I'm thinking of is I is equal to NQA times the drift velocity. If we rearrange this to solve for the drift velocity, we'll see that we can divide our current by the carrier concentration, the charge of the carriers, and the cross-sectional area. If we write out the math there, we'll see that when we put 1 amp divided by the charge of an electron times the charge carrier concentration times the area we end up getting a value of 3.5 times 10 to the negative 5th meters per second. And that ultimately is not that fast. If you think about what that number actually is, that's about 10 centimeters every hour. This means that the electrons are actually not flowing all that fast through a conductor under an electric field. But since there's so many electrons, 10 to the 28 electrons, this current is actually capable of transferring a large amount of charge in a given time period. Another useful quantity is the current density, which we use the letter J for. This describes the amount of electric current passing through some area. And so the units for current density would be amperes per meter squared. This is essentially the current divided by the area of your conductor. And this current density is useful for a variety of other electrical equations. And it's important to remember that the positive charges would move in the direction of the conventional current, but electrons will move in opposite the direction of the electric current since they're negatively charged. The electrical resistivity describes how much a material opposes the flow of an electric current. This resistivity is measured in the SI unit of ohm meters, and essentially something with a higher resistivity would cause for electrons to be bent more as they try to pass through that material. It makes it more difficult for charge carriers to travel through a resistive medium. And so ultimately we will see that once all of the current equilibrates and the charges begin moving in a constant fashion, that the electric force will be equal to a drag force that is applied by the resistive medium, pulling back on these charge carriers. Ultimately, this leads us to an equation that says that the electric field within a conductor will be equal to the electrical resistivity rho times the current density through that material. And it's important to note that electrical resistivity is an intrinsic material property. This means it doesn't matter how much of a material, how big my chunk of copper or silver is, the electrical resistivity will always be the same, strictly based on which material the electric current is trying to pass through. And here are some values, some common values for different materials and their electrical resistivity, which you will see is presented in units of ohm meters. This leads us to the electrical resistance R, which describes how much a specific sample opposes the flow of electric current. The resistance R is measured in the SI unit of ohms, which we use the Greek letter omega for. And to calculate the resistance, we will have to take into account the geometry of the specific sample that we're looking at and the specifics of the material. So the resistance will be the resistivity times the length of the material divided by its area. This means that a longer material, a longer wire, would have a greater resistance, and a wider wire with a greater cross-sectional area would have a lower resistance. Whereas resistivity was an intrinsic material property, the resistance is an extrinsic property. This means that it depends on how much of the sample we're talking about. The resistance will change based on the geometry of the sample and how large it is and how much of it we're actually looking at for the electric current to pass through. In a similar type of sense, the conductivity is the intrinsic material property that describes how easily electric current will flow through a material. So the conductivity is strictly the inverse of the electrical resistivity. So usually you'll just want to stick to thinking about the resistivity. This is one that we'll often rely on, but occasionally it might mention the conductivity, which is measured in Siemens per meter. This is like the inverse units of the resistivity. Or we could also measure a conductance, G, which is essentially the extrinsic version of the conductivity. The conductance is just the inverse of the resistance of a sample, and conductance is measured in Siemens. So similar to resistivity and resistance, the electrical conductivity is an intrinsic material property, and the electrical conductance is an extrinsic material property. So in solids, the electrons are the thing that actually conducts the electricity. And in reality, we have a three-dimensional solid which has atoms sort of arranged in a specific lattice structure. And as electrons try to travel through this lattice, they will be bent about by these different nuclei based on their attraction to those positive nuclei within the lattice. Ultimately, the energetics of the charge carriers within the material are what dictates how easily a material will conduct electricity. And we would say that there are two different types of electrons in solid materials. There are valence electrons and conduction electrons. The valence electrons reside in the valence band, which is a low energy state where electrons are tightly bound to the atoms, and the free electrons reside in a conduction band, which is a high energy state that allows for electrons to hop from one nucleus to the other. A lot of this is more complicated than what is needed for your understanding in this class, but it's important to note that insulators have a high electrical resistivity while conductors have a low electrical resistivity. On the other hand, we can have electric current transferred through a sample that is not solid. And in the case of ionic solutions, where we have ions in solution, the ions are charged particles that end up carrying the current. And so under normal conditions, the conductivity of an ionic solution is essentially proportional to the concentration of ions in that solution. Through a little bit of fluid dynamics and electrical equations, we can find that the conductivity of an ionic solution is based on the concentration of ions in solution, the charge value of each of those ions, divided by some hydrodynamic drag coefficient. This is the letter zeta, the Greek letter zeta, and it will often be given to you. We can use Ohm's law to relate the current and the resistance of a system by the voltage that is applied to that system. From now on, instead of using delta V as the symbol for voltage, we're just going to use V just to kind of eliminate some of the variables, but it's important to note that V here is a voltage. This is a potential difference that is applied to some material. And Ohm's law says V equals IR. The voltage will be equal to the current times the resistance for any electrical system. So essentially, the voltage is what is motivating charge carriers to move, and the resistance is what is preventing charge carriers from moving through a material. And ultimately, the current is a result of these two competing factors. We can see that when we change around the voltage that is applied, we're essentially changing the number of batteries attached to our electrical system. And as we change the resistance, we're essentially changing the amount of nuclei in the material that cause for electrons to bend their path as they find their way through a material. Essentially, we're putting more debris or more frictional material in the way for the charge carriers as they try to move through the material, and that will dictate how fast the charge carriers move through the material, what the current is. And when we talk about voltage, we're specifically talking about things like batteries, generators, solar cells, or wall outlets. These are all things that could provide voltage to motivate charges to move through an electrical system. On the other hand, things that carry current are typically like wires, copper, silver, tungsten, or filaments. And some common resistors would be things like light bulbs, the human body, or potentially nuclei within the atoms of a solid. So in this example, we're asked to find the electrical resistance of the human body by approximating the wingspan as a cylinder with length 2 meters, radius 10 centimeters, and the electrical resistivity of the human body is given to us as 2 ohm meters. So we start off by drawing our diagram. We're going to imagine the wings of this person, the arms of this person as a perfect cylinder, and the area of that cylinder would be pi r squared. We want to get that into the standard units first. We were given the length of this cylinder as 2 meters. We were given the resistivity of the material as being 2 ohm meters, and we were asked to solve for the resistance. So we find our equation. In this case, we could do R is equal to rho L over A and begin plugging in our numbers. In this case, the resistance of this sample ends up being 127 ohms just about. And so we can use this result to calculate what type of electric current would be physiologically dangerous for a human being to experience. And ultimately, the physiological danger of electrocution depends on the amount of current flowing through the human body and the amount of time that that current is flowing. We can use this chart down in the bottom right to sort of indicate what different levels of electrocution would look like. If we think about touching a live wire that is at 120 volts, that's like the power lines that bring power to our house. If you touch that for 0.1 seconds from the graph, we can see that 0.1 seconds at about 120 volts. Well, if we use Ohm's law and say V is equal to IR, we can figure out that the current is equal to V divided by R. So it would be like 120 volts passing through a sample with a resistance of 127 ohms. And we would find that the current in this case is about 0.94 amps. And so if we trace out that line right around 0.94 amps for 100 milliseconds, we would see that touching a live wire at 120 volts for even 100 milliseconds could potentially cause fibrillation in your body and serious damage. We once again revisit the idea of thinking about electricity as a fluid flowing through a system. The flow of electricity is a lot like the flow of water through a fluid system, where the voltage of an electrical system is a lot like the pressure that pushes the fluid through. The current is like the flow rate, the amount of actual fluid passing through a system, and the resistance is like the viscosity or the friction that would be felt. It's like the debris in the way that prevents the fluid from flowing through the system. So we have an analogy for voltage, which is essentially the motivating factor that causes for charges to move. And we know that positive charges move from high potential to low potential, from high voltage to low voltage. It's like a positive charge would roll down an electrical hill. And the stronger that voltage is, the greater the amount of charge would be flowing every second. And that's a lot like the current. How much current is actually contained in this river that's flowing. That's like the electrical current. And the resistance is a measure how much friction or viscosity that is experienced along the way. So if this current feels a lot of bumps and turns and prevents it from flowing freely, that would be like a very resistive sample. So electrical energy can be stored in an electrical system and later used to transform that energy into some type of useful work. This is ultimately how batteries work, by separating charges so that they can be recombined later in some type of electrical process to power a light. And just to be clear, all of our ideas about electrostatics are still true. The work done to separate charges involves a change in potential energy of the system and ultimately involves separating charges by some potential difference, delta V. There are many different ways that we could separate charges. For example, we could do it electrochemically, like you see with batteries. We could do it biologically with ion pumps around a cell membrane. We could do it Using electromagnetism with generators, we could separate charges and store up energy with a photovoltaic cell or some type of process that converts light to electricity. Or we could use heat to store energy with a thermoelectric generator. Any of these methods are ways of storing energy that can be harvested later. One of the simplest and most convenient ways of storing energy is in a battery, which is essentially an electrochemical cell that separates two different chemicals that will exchange their electrons with each other when they are put in solution together. Essentially, this involves a redox reaction, a reduction and oxidation of the particles in solution to allow them to exchange electrons back and forth and ultimately power some type of electrical system. Some examples of electrochemical batteries include copper-zinc batteries or nickel-cadmium batteries. So in an electrical system, batteries act as voltage sources, motivating charges to move and powering the electrical system. The most important idea, the most important quantity for a battery is its voltage. And for example, a AA battery has about 1.5 volts. That's how much voltage it can supply, whereas a car battery is about 13 volts. The electric power is essentially a measure of how much energy is transformed or converted in an electrical system over time. So as electricity flows through this light bulb, we will see that the electrical energy stored in the battery is given off as heat and light to the environment as we let that electric current flow through it. And so ultimately, this heat or energy that's being lost by the filament can be quantified as an electric power. And we could calculate the power dissipated by some medium by taking the current flowing through that medium times by the voltage applied to that medium. Now, using Ohm's law, we can also rearrange this in several different ways depending on which variable we're trying to solve for. The electric power is measured in watts, and 1 watt is equal to 1 joule per second. And just to be clear, make sure you remember that power is ultimately just the energy flowing through a system divided by the time that it took for that energy to flow. So if we think about several different light bulbs, we can think about a 25-watt light bulb. That's like this one right here, giving off a low power. And we see that also the color of the light somewhat changes. But a 60-watt light bulb has a much brighter light and gives off a lot more energy over time. In a similar sense, the compact fluorescent light, which is also rated at 60 watts, gives off the same brightness, but consumes much less power. Electrical transformers are a way of converting electrical signals between different voltages. This is ultimately what these large electrical power plants look like outside of a city. These transformers are taking high voltage electrical signals from a power plant and stepping it down to be at the voltage level that is useful for household applications. A transformer will always involve two coils being electrically linked together, and these coils are essentially used to either step up the voltage to a higher voltage or step down the voltage to a lower voltage. And you'll see that essentially a step down transformer or step up transformer just depends on how many turns we have in each of these coils. So there will always be a primary and secondary coil, a first side of the system and a second side of the system. And by energy conservation, we know that the power flowing through each side of the system has to be equal at all points in time. And this means that we have an equation that can be used to dictate how much the voltage will be set at for a different transformer configuration, depending on the current flowing through each side of the transformer. So essentially, a transformer will take either a low voltage signal and turn it into a high voltage signal like you see here, or the reverse could also be true. So here we have an example talking about how power is lost through power transmission lines as it arrives at your house. Let's think about our house, which draws 10 kilowatts of electrical power from a power line, and the power line has a resistance of 1 ohm. Let's ask ourselves, how much power is lost in two different transmission lines, one that is operated at 240 volts and one that is operated at 14 kilovolts. This would be like a high voltage line, and the 240 kilovolts would be like a low voltage line. So let's go ahead and think about our equation. For a transformer, we have I1 V1 is equal to I2 V2, and we will label the low voltage system as our second system, and we'll label the high voltage system as our third, with the house being our first system. So The house operates at 10 kilowatts. That is 10,000 watts for the power over here. And for the second low voltage power line, we could figure out the current that is flowing through that by plugging in the voltage for that power line. We would see that the current flowing through this low voltage power line can be calculated as 41.7 amps. On the other hand, in the high voltage power line, we would say that our house is operating at a certain power, and we can figure out how much current is going to be flowing through the high voltage line. If we plug in our power from our house, we can solve for the electrical current flowing through the high voltage line at 13,000 volts. And the current flowing through the high voltage power line is 0.72 amps. Now we can calculate the power lost by each of these power lines in these situations by using I squared R for that power. And we can calculate the power lost in the high voltage line by using I squared R at that current. So the power lost in the low voltage line is about 1,700 watts or so. And the power loss in the high voltage line we can also calculate is about 0.5 watts. In this way, we see that a lot of power is lost when we transmit electrical signals at low voltage. And this is why power lines and transmission lines are set to be at extremely high voltages, because high voltages travel farther with lower power losses. However, we do need to use transformers to step down this high voltage so that it's actually useful for household applications. So that'll cover everything for our unit on electric current and resistance. The equations are a little more manageable, and these will build toward our next unit of circuits, so stay tuned. I'll see you in the next one.